我们就开始这周的理论物理报告啊。今天我们很开心邀请到了新加坡国立的李金华教授给带来这个星期的理论物理报告。我先简单介绍一下刘老师。刘老师是斯坦福大学齐小亮老师的学生，博士生。然后他20年加入新加坡国立，然后现在是leading the group in non-Hermitian phenomena as well as simulation on classical and quantum circuits。我想我就不啰嗦了，然后我们李老师给大家今天的精彩的报告。
Hi everyone. Okay, I'm so sorry I have to use English because although I can speak Chinese, but maybe I've tried doing the speech in Chinese, but maybe some people say it doesn't sound very professional. So please allow me to use English for this talk. Okay, so very nice meeting you, and thank you so much for coming to my talk on a Friday morning, early in the morning. I know some of you have even traveled some distance here, and thank you very much. Okay, so I'm Qinghua from NUS, and I'm going to basically give you a talk about some new ideas about non-Hermitian physics. And if in the background, you can see that that is, the faint picture of the National University of Singapore. Okay, maybe it looks quite similar to many other campuses in this picture, but okay. Okay, yeah, so although my talk might seem to be very interesting, I have to say that most of it is, of course, the hard work of many of my group members and collaborators. So I think this picture was taken a few months ago, maybe when actually some of you, a few of the audience are actually around here. And yeah, so I thank my group members for the results that I'm going to talk about. And so about the content, so about non-hermiticity. So I understand that this is, although this seems to be quite a popular topic, but when I talk about non-hermiticity to, let's say, my colleagues or collaborators, usually the first question that people want to ask me is that, is it physical? Because after all, say, since undergrad, usually we are taught that Hamiltonians have to be Hermitian because if you have a non-Hermitian Hamiltonian, the eigenvalues may be complex and it may not make sense, right? And is that really true? Okay, so let's look at what is on the slide. So if you see, actually, there seems to be many physical systems that are not really sort of energy conserving, and they exist. So for example, let's say possibly the simplest example of a non-Hermitian Hamiltonian would just be the time evolution operator of a system with friction, let's say with damping, right? So for instance, if you have let's say a ball and spring system with a damping, you write it let's say, the Newton's law has a dissipative term. And if you write it in terms of the first order differential equation in time, right? Then the operator that controls the time evolution is a non-Hermitian Hamiltonian, right? And of course, if you go further to say, talk about, let's say photonic systems, then I think it's quite well known that you will have like lasers and all this that are non-Hermitian because there is gain medium. And of course, not just that, if you are talking about electric circuits, right, then there are also many devices that are sort of non-reciprocal and non-Hermitian. For instance, you have operational amplifiers with all these external, let's say, sources which are connected to the outside. So that means the energy is not conserved. And for quantum systems, of course, if you were to couple them to external reservoirs, there are also well-established formalisms that go beyond the Hermitian paradigm. And last but not least, is a non-Hermitian Hamiltonians or non-Hermitian operators can also be used in other kinds of complex systems, for example, like random walk systems, cellular automata, and so on. And most of them sort of they don't really generate like Hermitian time evolution. So anyway, the whole point here is just that if we describe physics, not just standard quantum mechanics, but if we just talk about, let's say, physics in general, then there are so many different phenomena that can be modeled by non-Hermitian operators. So now the next question that people would ask is, so what is so interesting about non-Hermitian physics? And of course, there are many people will give many different answers. Some of you may also have your own sort of like topic, your favorite topics. Yeah, but maybe I will just highlight three different sort of themes. So the first is about that enlarged symmetry classes. So the main idea is that because the non-Hermitian Hamiltonians have complex eigenenergies, and complex eigenenergies live in a complex plane, which is a 2D plane instead of a 1D like real line, right? Then the idea of gap also has to be generalized. So for instance, you can have an energy band that actually encircles a certain region on the 2D plane, right? Of course, there's no Hermitian analogy. And you can see that because of that, right, it's possible to define something called a spectral winding about, let's say, some like the origin or about any point you want. And this is called a point gap. And of course, this type of point gaps has its own sort of manifestations of topology. So later I'm going to talk more about that. Like what is the physical in the sort of significance of a point gap? And I also want to mention that even for usual line gaps, it's also not so straightforward now because it's possible for two bands, which are like two clusters of states, right, to be separated by, let's say, like a line that doesn't have to be sort of parallel to this imaginary line. Meaning that it's possible for, say, have let's say a transition between, let's say, two bands that are separated. Let's say one is positive energy and one is negative energy. With, let's say, another case where the one is like positive imaginary and negative imaginary, so on. Yeah. And perhaps even more interesting would be the idea of exceptional points. So the idea is that because these energy eigenvalues are complex, right? So they actually form a complex Riemann surface. And as we all know, Riemann surfaces they can sort of cross at so-called branch points, and they can form branch cuts. Right? And so complex analysis, we know that when we have this branching, like let's say bands, they are, if you were to encircle it, like say once, you may not go back to the same surface. In this picture, actually, if you were to encircle it twice, then you go back to the same surface. Right? So non-Hermitian systems naturally can harbor this type of interesting band structures, these features. And we can also show that other than the fact that you don't go around to the same point after going around once, you also have, say, heightened sensitivity because of this square root or cube root or n root singularity. And later in my talk, I'm also going to say how it leads to something called negative entanglement entropy. Yeah, which is one of the highlights of the talk. So another theme I want to talk about is this non-Hermitian skin effect. So I think many of you have already heard about this. Yeah, so basically this is about the very sensitive nature of certain non-Hermitian systems. So just to give some introduction about what the non-Hermitian skin effect is about, right? So the idea is that if we have, let's say, lattice hoppings that are asymmetric, then you will actually get very high degrees of sensitivity because the states will all accumulate to one side. And this accumulation requires the presence of boundaries or impurities. So for instance, let's say if you look at this model, which is the simplest possible example, that's called the Hatano-Nelson model. So you can write in this form where z is e to the ik, and if you draw the model, it's basically just a simple hopping model where one direction is stronger than the other direction, right? So intuitively, you can see that if you have any wave packet and you try to time evolve it, right, you'll see that because it's asymmetric, so in general, the states will just all be pumped towards one direction. And you can show that if there is a boundary, then it will be pumped to one direction until it kind of stops here, right? I mean, until it reaches a steady state that has an exponential profile. So this it's important to note that this is not just for one particular state, but in general, you can show that no matter what initial state you start from, if you were to wait long enough, actually you don't even have to wait for so long, you will be able to get a steady state profile that looks kind of like exponential. So we might be wondering, so how do we mathematically represent this exponential accumulation? What is the significance? So maybe we first look at the energy spectrum. So here I'm showing you the sketch of a PBC, the periodic boundary condition spectrum, and the open boundary spectrum with the boundary. So the interesting thing is that you see that this OBC spectrum is very different from this PBC spectrum. Right? For the PBC spectrum, it's quite easy to find out like how it should look like because you can substitute, let's say, e to the ik when k goes from 0 to 2 pi into this formula for the energy dispersion, and naturally it looks like an ellipse, right? But it turns out that if you were to, let's say, remove the boundary coupling from, let's say you tune it down from 100% to 0%, that means you interpolate from PBC to OBC, you will find that this ellipse will actually shrink and eventually until it becomes a line at the center, I mean a line on the real line. So at this point, I want you guys to take note that this is something that is actually quite counterintuitive, because let's say if you have a system with millions of hoppings, right, and you just remove one of the hoppings. Say for instance, let's say if you have millions of hoppings and you put it in a chain, and then you just remove or you just take away one of the hoppings, right? Intuitively, we might think that this may not do much because it's just one hopping out of the millions or billions of hoppings. But actually, that one hopping is enough to actually change the energy of every eigenstate. I mean, it's not just one state, it's all the eigenstate changes. So why is that so? So the reason why is because if you were to take away the boundary hopping, right, what happens is that the dynamics will just be frozen here. That means the amplification will be frozen by the boundary when there's a boundary. But if there's a connection, let's say a connecting hopping here, then the amplification will just go on and on and on. So you can see that for non-Hermitian systems, at least those that are non-reciprocal, it's like the fact that you change one hopping, or even the fact that, let's say, if you were to introduce one impurity, is enough to change the long time dynamics. So you can think of it. So this is the physical sort of origin of why non-Hermitian systems can be very sensitive. Now the next question will be that, so how do we find like what is the OBC spectrum? Let's say the PBC spectrum, we know how to solve for it. How to solve for the OBC spectrum? So later I'm going to talk more about this, but for now, let us just note that one of the most established ways of expressing this boundary accumulation is actually by using a complex momentum. What does that mean? Okay, so if you look at this block state, I mean the non-block state, right? I mean the exponentially localized state, and you look at the profile, yeah, I think there's a typo, there should be X here. Then you see that in order to accommodate, let's say, correspondence between the energy dispersion and the OBC spectrum. So just to remind you, so usually when we talk about energy dispersion, we are saying that, okay, we have this, let's say, a polynomial that represents this that's the usual energy eigen equation. That's the determinant of H, which is Hamiltonian. Z is e to the ik minus energy equal to 0. Right. So this is something that's just given directly from the model's hoppings. But of course, now we know that if you just naively substitute z equal to e to the ik, you don't get the OBC spectrum, you only get the PBC spectrum. And the OBC spectrum is actually derived from the PBC spectrum by someone doing all this collapsing mechanism. But this is not a very sort of a straightforward process. I mean, it's like, if you want to predict the exact shape of this OBC spectrum, it turns out that it is actually not straightforward to get it from this form, the algebraic form of PEZ. So actually right now, we are actually doing some kind of a machine learning approach to, I mean, in my group, to do this classification. So why machine learning? It's because if you think about it, this is a bit like a facial recognition kind of task, right? So you can think of it as the dispersion polynomial is like the name of this model, and the label of the model. And all these are like the faces, the images associated with this OBC spectrum. Actually, what we need extract is the graph structure, the graph topology. And it's not a one-to-one mapping, quite interestingly, because it's possible for, let's say, two different models to somehow coincidentally have the similar graph topology. And it's also possible, of course, for two different graphs. So I mean, for the same polynomial with different parameters with different graph topology. Just as it's possible for two unrelated people to have the same name, right, but different faces. Or it's also possible for, like, let's say, identical twins to look almost alike, but although they are different people, something like that. So I just want to comment that also, in case you're thinking that this all look very symmetrical, I want to say that if you take almost any non-Hermitian model, right, and you kind of do some conformal mapping in the complex plane, you should be able to get one of these sort of standard graph topologies. Well, this is not all, this is just a few from my paper. So usually when I talk to people about this rich spectral topology, right, one question people will ask is about, so is this physically significant, right? That means, why do we want to care about this spectral graph topology? And the reason is that spectral graph topology actually can have a non-trivial response behavior. It can lead to non-trivial, let's say Berry curvature and linear response. So for instance, let's consider a 2D model. So this 2D model from this paper, and this model is designed to have Chern modes, right? Where this ky is a good quantum number, and this is a complex plane corresponding to the OBC spectrum of in the other direction. So this is like a cylindrical boundary conditions. You have OBC in one direction and PBC in the y direction. So this model was designed such that we have, let's say, a y-shaped spectrum, let's say for some values of ky, and then after that it changes to some other shape. I think it's an inverted y shape or something. And then there's some sort of topological, some transition in this graph topology. So we're not talking about the usual, let's say, topological transition when you close the gap. So here the gap never closes, right? This is one band and this is another band. The gap never closes. Only the spectral topology of the OBC bulk changes, right? But yet when you do the computation of this Berry curvature, we see that there are actually some discontinuous lines, right? So for instance, let's say there's some discontinuity here and here. It corresponds to where the graph topology actually changes. And then in the x direction, there are also discontinuities, and that is actually what happens because of this. So remember, because let's say when you do this deformation, right, it turns out that the complex k that That means the deformation to the complex plane of the momentum, right, actually has some discontinuities. Let's say when you want to navigate these different branches. That's why we have discontinuous Berry curvature, because locally it's just at the rate of change of the eigenstates as a function of the underlying momentum just has to change discontinuously in the complex momentum loop. So not the real momentum, now is defined with respect to the complex momentum called the generalized Brillouin zone. Of course, I mean, this looks like maybe I chose the color, so this is called the avocado color palette in Mathematica. So yeah, it maybe looks like a cut avocado. And so in this paper, we propose a co-atom setup where we can where we can measure sort of this type of the physical signatures of this type of Berry curvature, this continuity through these response kinks. And that's just because this Berry curvature, right, they behave a bit similarly to the magnetic field. And you can imagine that if the Berry curvature has a discontinuity, there will be a sudden impulse as you, let's say, travel to the other part of the Brillouin zone. Let's say the wave packet will go like this, then here you will encounter an impulse, and here you get an impulse as well. So before I go on to talk about some other aspects of non-hermiticity, let me just share with you one sort of slide, one sort of interesting slide on this relation between the non-Hermitian skin effect with electrostatics. So just now when you look at these figures about this PBC spectrum in the ellipse, and let's see you have OBC spectrum inside, some of you might actually recognize it as resembling some electrostatics problem. So the question is that, is there really a link between them? Interestingly, the answer is yes, right? So in this paper, we showed that actually, if you were to identify this kappa, which is the imaginary part of momentum, or the inverse decay length of the skin mode, right? With the electrical potential or voltage, right? Then you have a nice correspondence between this. So now the energy is just a position of in the electrostatic system, right? And then we also have the kappa corresponds to V. And then interestingly, the density of states in the non-Hermitian system actually directly corresponds to the density of the electric charge. So which means that if you were to, let's say, take this electrostatics problem, right, and you do use a PDE solver, let's say for the Poisson equation, right, what you will get, it should be mathematically sort of similar to, mathematically identical to the solving this skin effect problem. So here, to complete the identification, we know that the kappa equal to 0 curve, kappa equal to 0 means there's no skin accumulation, just means PBC spectrum, right, will correspond to this V equal to 0 curve, which is just an equipotential. Maybe you can call it a conductor, like equipotential. And then of course, the OBC spectrum will be the charge density, because I say that this density of states corresponds to the charge density. So in this identification, it becomes that let's say if I want to engineer a certain non-Hermitian system with a particular PBC spectrum and a particular OBC spectrum as well, given by let's say some charge density, right, and some density of states, I just need to draw the equivalent system in this electrostatics picture, and I use the Maxwell equation solver. And after solving for it, I'll be able to get, let's say, the induced charge density on the PBC loop, right? Yeah. And the induced charge density would give you the density of states on the PBC loop, which will in turn give you the energy dispersion, because it's just which energy dispersion here is related to the E decay inverse, right? I mean, the density of state related to the E decay inverse, which is the gradient of this density of the dispersion. Okay, so this is not the conclusion yet, but in fact, it's just not the beginning either. Okay, so just now I have given something like a tour of some aspects of non-Hermitian skin effect. And now I want to discuss about, let's say, going beyond that, right? So there are some open questions. We might not have time to do everything, but I'll try. So first question is that, what happens when there's many body interactions or few body interactions, right? Because just now I was just talking about everything about just at a single particle level, right? And the second one will be that, what happens when you don't have OBCs per se, but if you have, let's say, arbitrary spatial inhomogeneities? Because for instance, the OBC, you can think of it as like a step function in the hopping strength in real space. But what if you have, let's say, some impurity potential or something, right? That means, is there like a easy way to generalize this idea of the skin effect? And also, the third one is more technical. It's about when does this well-established GBZ theory sort of get violated in a significant way? So in the rest of my slides, I'll attempt to answer some of these questions. Of course, partially answer them by covering certain things like, say, like generalizing the skin effect to Fock space and so on. Yeah. So about the interactions, right? So first, let me share with you actually, this looks like a very simple identification, although it's actually quite useful. So let's say if I have just a system with two particles, right? One easy way to understand or visualize that is to just draw in a configuration space. Say, for example, this is the coordinates of the first particle, this is the coordinate of the second particle. So now I've just mapped from this 1D two particle system to a 2D one particle system, right? And of course, now the hoppings, for the first particle will be the horizontal hoppings, and for the second particle will be the vertical hoppings. And now I think the one interesting thing that is useful for identifying with the skin effect is that even if your system doesn't have physical boundaries, right? Let's say the system is just a PVC system, as long as there are some sort of particle interactions or particle statistics, right, you will still have effective impurities or boundaries. So for instance, let's say if the particles are forbidden to be on the same position, right, then it means that this line is out of reach. This line cannot be occupied. And that means that now you actually have an effective boundary, right? So what happens is that, let's say if you were to investigate, let's say, the non-Hermitian skin effect in this type of systems, you find that there is we just get the simple idea that there is something called the non-Hermitian skin clusters, where instead of the particles accumulating against a boundary, now they are just accumulating against each other, right? So it means that if the skin state is actually against this line, then it just means that it's one particle it's something like if one particle has experience a stronger skin effect than the other particle, then they eventually kind of like power against the other one. Of course, this can also be generalized to a higher number of particles. But even for 3 particles, it could already be quite interesting, because for 3 particles, let's say if you have a model that has, let's say, this type of that means some kind of interactions such that they form some loops in this configuration space, right? You'll find that this can be interpreted as some feedback cycles. And these feedback cycles, of course, in the original language, it will just be some interparticle interactions, some special ways that they interact. And although I'm not going to talk about this in detail, but if you look at this paper, we showed something that's different from the usual skin effect, in that usually we talk about the non-Hermitian skin effect in the real space. But it turns out that, let's say, for those of you who are familiar with quantum scars, right, the idea is that you can, let's say, partition this, the Hilbert space into, like, let's say, segments with different Hamming distance from the scar state, right? And then, although each segment actually has a lot of states, like it's macroscopically, I mean, there's a macroscopic number of states. But it turns out that if you were do this, you find that it's possible that to engineer the system such that the overall that there's like a net hopping with net asymmetry in the hoppings from some parts of the Hilbert space to another part of the Hilbert space. And that could counterintuitively lead to some enhanced quantum scars due to this non-hermiticity. And just as a direct application of what I said just now, right, it's possible to, let's say, just write down a Chern model, right, in terms of two interacting particles. So of course, this looks a bit artificial, right, because for the use, let's say if we start from some Chern model on the checkerboard like this, you can, by interpreting two particles as, I mean this as two particles in 1D, you can write down all these weird looking interactions. Yeah, but this, although it looks weird, it's actually possible to physically realize them. So as I've shown in a previous work on the quantum computer, so we're fortunate enough that we had access to this IBM from quantum computer, yeah, at least for my university, right? So it turns out that on a universal, like there's a digital like universal quantum processor, it's possible to simulate, I mean, in principle, any unitary that you want. So, or even non-unitary systems with a post-selection. So it's possible to simulate, let's say, some weird looking models. And one thing that we realize here, I mean, this Hermitian, that we can, let's say, measure this wave packet evolution along a diagonal boundary. And the results look quite promising. As in, you really see that the center of mass of this wave packet really changes like monotonically with time, which is a strong evidence that it's possible to at least observe this chiral motion on a quantum computer. So this is just some additional data that shows that that there's some kind of chiral propagation as a function of time. So this is the exact calculation, and this is the hardware measured on the quantum computer. So I just want to say that because this was done in 2022, and subsequent to that, we lost, I mean, we kind of lost access to the quantum computer for some time. But right now, like in the recent times, I mean, that this year, we managed to pay for this access again, and now they have much better systems, like with more than 100 qubits. And so maybe as an open invitation, if anyone is interested to, let's say, have some weird looking models and was interested to collaborate, maybe we can help in some way in realizing your model on this 156 qubit in quantum computer nowadays. Yeah. And yeah, this is some, I would say just some schematic that shows that we could even realize, let's say, 4D higher order topological systems on a quantum computer. So of course, the idea is also first to map this 4D system into a 1D system with 4 interacting particles. Yeah. So of course, because I mean this mapping works because if we are talking about a non-interacting system, right, at a single part, originally at a single body level, of course, the whole Hilbert space is kind of wasted, right? That means there are so many, like sort of many body sectors that are not really used. So in this sense, it's actually not surprising that we can map it, like sort of compress a very big system like into a very small lattice with interactions, taking advantage of this the full Hilbert space. And like through some tricks, we could sort of recompile the circuit and so on to make it more sort of feasible to realize with sufficiently sort of a small circuit depth. Yeah. So just to summarize this part, right, I want to say that in general, like certain mappings are useful in either understanding the skin effect of interacting few body systems, or to realize their sort of so-called physical sort of realization on the quantum computer. So by the way, in some papers people call these experiments, but so there was once the first time I submitted this, in the cover letter we say it's experiment, and then PRL they came back, the editor said that, oh yeah, you shouldn't call this an experiment and so on. So, but luckily they still gave us a chance if we change the wording. So I'm just saying this is not really an experiment because we are not the ones who do the experiment. We're just using other people's quantum computer. Okay. So just to extend what I was talking about just now, you might have the impression that we are only doing few bodies, but actually, I mean, computational power when the computational power is available, of course, we can also talk about let's say the non-Hermitian skin effect with more particles. For example, a half-field system. So for the half-field system, let's say a fermionic system, we know that they have this Pauli exclusion, right? And the non-Hermitian skin effect doesn't just act the same anymore. Because let's say if you have one particle, of course the skin effect will pump towards the boundary, right? And with a stronger kappa, with stronger skin effect, it becomes more localized. But then let's say if you have the Pauli exclusion in a half-field system, it turns out that you get something called what we call the Fermi skin. Yeah, as you realize on the quantum computer as well here. What happens is that as you increase the strength of this non-Hermitian skin effect, right? You will actually the profile will tend towards more like a Fermi Dirac kind of shape rather than like a exponential shape, localized shape at the boundary. Of course, that's just because of Pauli exclusion. In our paper, we have some analytic results on that, and more importantly, extensions to the let's say many-body interactions. So it's also interesting that if you want to try to do some curve fitting to sort of fit this effective, sort of the effective inverse temperature of this profile with the non-Hermitian, let's say alpha is the non-Hermiticity strength, which is kappa in the previous slide. It turns out that this effective, sort of the effective temperature of this is actually proportional to some alpha. I mean, other than the original physical temperature, yeah, it is also it's proportional to this physical temperature plus some quadratic correction to this non-Hermitian strength and so on, and some coupling between the two. So, but one thing I want to say is that this is still not the same as physical temperature, because when we talk about the usual sort of Fermi surface, right? We are talking about Fermi surface as local, that this is a profile in an energy space. But in this context, we are talking about profile in a real space. So it's still not the same thing. Yeah. So there are some quantum computer results. So this is the Hartano-Nelson. For the Hartano-Nelson model, we are the exact results when you have an initial state at the center, and if you have gamma like equal to 0, no non-hermiticity, you get a sort of a balanced sort of time evolution in both directions. But with a non-Hermitian skin effect, it will just the eigenstate just so I mean the initial state just goes in one direction here. And this is sort of closely replicated with the IBM quantum hardware. And you can also see this clearly through this center of mass sort of evolution between, let's say, the green one is for this with non-hermiticity with the skin effect turned on, and this yellow one is really turned off. So we see that the accuracy that we can get is much higher than the uncertainty. So I mean much higher than that means the uncertainty that we have is much lower than the difference between the Hermitian and non-Hermitian cases. For the SSH model, it was harder because the model is more complicated and we have fewer unit cells. But nowadays, we can do much better. So as a summary to this part, right, I just say that basically we can use Fermi skins to the Fermi skins sort of profiles are representative of the interplay between Pauli exclusion and the non-Hermitian skin effect. And then we can use quantum computers to realize a variety of such effects. So in fact, here there are other papers. I mean, this one is with Wen Tan, which is Wang Zhong's previous student, and some other And then recently, we also realized this some kind of SPT classing easing transitions. Right now, we are also realizing that some of these Wen Xiaogang's plaquette models and so on. So now let me move on. Okay, so I think, okay, I don't really want to talk for 1.5 hours. So maybe we'll go a bit faster now. So talking about inhomogeneous skin effect systems, right? So let me just show you some pictures. So this one, I won't go into detail about this. Yeah, because I think it deserves a separate talk on its own. I just want to say that I want to talk about how we can understand, how do we think about this problem, right? So inhomogeneity in space and non-hermiticity, these are two different things, right? If you have one of these ingredients on its own, for example, there's inhomogeneous, inhomogeneity in the hoppings. That means different hoppings at different positions have different strength, right? When it's Hermitian, for instance, what you get, of course, is still the real energy spectrum. So if, let's say, we have this GX, that means the hopping strength being stronger at the sides than at the center, then we, of course, your eigenstates will also generally look different, right? So, so actually now we are doing PBCs. The dotted lines it represents PBCs. So you see that in general, like there are some states that are localized here and some states that are localized at different. Yeah. So you can also think of it as some kind of Werner-Stark localization. Yeah. No, not exactly, because usually when we talk about Werner-Stark eigenstates, they correspond to inhomogeneity in the on-site term. But now we're talking about inhomogeneity in the hoppings. Right? And another thing is that, okay, let's say if we have, on the other hand, if we only have non-hermiticity but no inhomogeneity, then your GX is actually like a constant. And then you have this Hartano-Nelson model, and the states are all sort of uniformly distributed, just because there is no inhomogeneity. Now, the interesting thing is that if we have a combination of both, that means we have asymmetric couplings, that's non-Hermitian, and we also have spatial inhomogeneity in their strength. Then in general, we will find that there are some states that are like complex and some states that are real, right? But now, the thing to emphasize is that these real states, right, they actually exist, right, even if there is no boundary like thing at all. So for instance, if let's say from here, let's say if I were to add a little bit of spatial inhomogeneity in the system, in the non-Hermitian system, right, you might think that this little bit of non-hermiticity is not going to do much, right? But in fact, you can already show that just a little bit of inhomogeneity in the hopping terms is enough to give you some real eigenstates that behave like OBC eigenstates. So it means that in non-Hermitian skin effect systems, right, OBCs is sort of I think the correct way to think about OBCs is not that it has to be a hard boundary, but it's more like an impurity. So for instance, if you look at this, right, it's like, so now let's say if the skin effect is pumping in this direction, and there is let's say inhomogeneity here, meaning that these hoppings are a little bit weaker than the other hoppings, right? Then it turns out that although there are some states that will still tunnel across it, but there are also many eigenstates that will actually be completely blocked by this part already. So maybe another way to think about it is that the spatial inhomogeneities in non-Hermitian skin effect systems, they have a very, very strong so that like ability to block the dynamics. So in this paper, I mean, I'm not going to go into this in any detail, but in this paper that we had recently, we showed that we can actually formulate something called a position-dependent GBZ, or a GBZ in phase space. Phase space means it depends on both position and momentum. And this GBZ is defined in this way, such that the eigenstates are given by this gamma x, which is this is the usual gamma for OBC. But now we have PBC, and then we have this correction term that is actually it can be actually not just a norm, it can be a very big correction. So this correction term, right? Okay, yeah. Sorry about it. So the idea is that now this kappa x, right, which is the kappa of this the log of this beta here, right, which represents the complex momentum, the part, it actually has a position dependent part that could be either real, such that the whole thing could either be real or complex. So that means for some values of gx, maybe your Cauchy inverse will not be real. Some parts of it will be real, right? And as a simple illustration, I show it. Let's say if you have a model that is gx and looks like that on the Hartano-Nelson model, right? What you see is that at different energies, you have different GBZs. For example, let's say if you have this E1 here, right, which is real, right? What happens is that this E1, right, is actually smaller than the 2gx of this inhomogeneous. That means it can be bigger, or either bigger or smaller than the 2gx that characterizes the hopping strength. So for example, if you have certain parts here, right, let's say that means at certain positions the kappa is real, but at certain positions the kappa is 0, but certain positions kappa is non-zero. So you can think of it as like that this whole system, right? The eigenstates, they don't have a uniform kind of a decay length, but at different parts, at different positions, they have a different sort of decay. For example, at some positions, it has here, this is like an exponent, some decay rate that is position dependent, and this one there is no additional decay rate other than the gamma. Yeah, and finally, I think maybe if there's one take-home message about this is that when we have two solutions, let's say when it's possible to have two solutions of this kappa at the same x, right? The actual physical model will the physical eigenstate will only choose one of these solutions. So for instance, let's say it's from a numerical eigenstate, you can possibly show that, okay, let's say you can just work backwards and find that the kappa could be, let's say, positive at some position, and suddenly it becomes negative at some position. Right? So what this means is that because kappa is the inverse decay length, right? So it means that if a kappa suddenly switches, it means that the exponential decay direction actually changes suddenly. And what is that? So something that it just changes suddenly, right? It's just like an impurity profile. So what this is trying to say is that spatial inhomogeneities, very smooth spatial inhomogeneities, can still lead to very sharp, let's say, sort of very sharp, let's say, kinks in this eigenstate profile. So to summarize this part, okay, at least I think I'm speeding up. So now So to summarize this part, so basically we are trying to say that we now have a formalism for understanding the non-Hermitian skin effect, at least for a simple hopping model, like nearest neighbor hopping model in phase space, right? And then the idea is that interesting is that the GBZ could have different branches, but the actual eigenstate will only choose one of the branches, and it can jump between the branches, leading to, let's say, I would say, very abrupt, let's say, abrupt kinks in the profile that is not even present in the model. That means the model looks like a very smooth model, but the eigenstates could have very sharp kinks, right? But of course, there's a lot of more work to be done because we didn't take into account of, let's say, the different hopping, let's say higher dimensions, like further hoppings and so on, where we have other things such as GBZ fragmentation and other things. Yeah. Okay. So now I'm going to go to I would say somewhere nearer to the last part of my talk, although it's still a bit long, which is about sort of violations to this GBZ. That means models. So now we're talking about models or systems that no longer behave like usual skin effect systems, although they are non-Hermitian. So one thing I want to start from is about this idea of exceptional bound states, which is about this band flattening projector. Right? So just to be clear, right? So exceptional bound states are special states of the band flattening projectors, not of the Hamiltonian, right? So usually when we talk about bound states, we talk about, let's say, for example, skin states, impurity states, or let's say topological boundary states. They are all eigenstates of the Hamiltonian. But if you look at the band flattening projector, right, you find that which usually should have energies of either, eigenvalues of only 0 and 1. We find that there is a special class of states that are known that can be very far from 0 or 1, and they exist precisely when the system has exceptional points. Right? So maybe this is something that is maybe not so well known about exceptional points, that exceptional points band flattening projector has some special pair of eigenstates that are very far from 0, that could be very far from 0 and 1. So let me just briefly introduce it a bit more. So let's say if I have a Hamiltonian that has an exceptional point in momentum space, right? It looks something like that, as I've shown. That means there's a branch point and there's a branch cut here, right? So what we want to focus on are exceptional points in momentum space. Of course, in the literature, there are many experiments and people talk about EPs in parameter space, right? But it turns out that if they are in momentum space, it's more interesting because when we go to real space, we need to perform a Fourier transform. And this Fourier transform could have very interesting behavior because of this singularity. So to understand this, how this singularity is, right, of course, we introduce this occupied band projector or the band flattening operator, which projects into one particular band. So we all know that these exceptional points they are defective at this branch point, meaning that defective means that at the branch point, there's only one eigenstate. It's not that there are two eigenstates. So it means that this projector must be well U-defined in some way, right? That means when k equal to 0 here, we expect this to kind of be U-defined in some way. Right? So to realize, to understand why they are U-defined or how they are U-defined, we borrow this idea from let's say from actually when the calculation of this free fermion entanglement spectrum, where we project this or we truncate this P into on real space, we cut away some region and see how much it deviates from being a projector. So for instance, let's say if we have a usual system that doesn't have an EP, right? Is that in general, in real space, the matrix elements of this P operator, which is this band projection operator, is sort of, it doesn't decay I think this is a bit exaggerated in some parameters, but it decays fast. Idea is that it decays fast and the non-locality is not sufficient to make the eigenvalues far from 0 and 1. We know that if this is gapless, right, that there will be some eigenvalues that are inside here that are logarithmic, leading to log entanglement entropy. But it's not as extreme as when we have exceptional points, where it turns out that these matrix elements could be super highly non-local. It could even decay slower than the power law. And it turns out that this will lead to some additional eigenstates. So just to firm up the terminology, right? So we call these special eigenstates as exceptional bound states. So to understand why they could happen, right? We can think in this way. So this the matrix elements of this P operator, right? Or the band projection operator are none other than these 2-point functions, right? And if you were to do a real space truncation, right? You can think that, okay, maybe if the hoppings are really too non-local, what's going to happen is that they might sort of, you can think that if you want to hop out of this the cut region and hop back again, maybe some information might be lost. Just because it turns out that some of the hoppings are so huge. Let's say hopping out is very large, but hopping back is back hopping is very, very small, right? So it leads to some kind of non-conservation of probability. I mean, this is a bit hand wavy. Yeah. And I want to say that although these hoppings are definitely asymmetric, right? In fact, they're highly asymmetric, right? More asymmetric than most of these skin effect models that we have seen. But one important thing is that there is no skin effect at all. And the reason why there's no skin effect is because this at the PBC level, right? When periodic boundary conditions, right? Your eigenvalues are just 0 and 1, right? So when eigenvalues are 0 and 1, it means they are already one dot. There's no loop for it to go into, right? But yet, when you go to OBC, which is in this case, the analog of OBC is just having a cut, then you actually see the new states coming out. So it's like for usual skin effect, it's like when you do a real space truncation, the states go inside the PBC spectrum. But then in this case, it actually goes outside, which is like the exact opposite of what happens in the skin effect. Right? I just want to say that this is not specific to quantum context, right? That means what I'm saying so far, this is, although people use entanglement spectrum to talk about this, but it's actually, we don't need to talk about entanglement at all. This is a property of a non-local matrix. I mean, a matrix of non-local elements, and that's it. Yeah. Oh yeah, maybe I should give some credit. So this actually came, okay, so actually during the COVID period when we were all alone and I was just reading papers alone at home, I realized there was an interesting paper, this paper by Shinsei Ryu and collaborators, and it talks about this negative entanglement entropy of the non-Hermitian SSH model. And so then I got very interested in this topic. And I thought that, okay, so why is it negative? Is there a fundamental reason, right? And then after that, I finally realized that it's actually because of the exceptional point. Yeah. So it turns out that as long as the system, it doesn't have to be any SSH model. As long as the system has an exceptional point, in general, you will get this kind of special eigenmodes that will give you a negative entanglement entropy. So because if the P lies outside of 0 and 1, you can show that the contribution is negative. Anyway, just to be concrete, right, I will show a certain like a simple parameterization. So let's say if I have a model of this form, such that A goes to just a constant, and the special K equal to 0. Right. And then B goes to, let's say, K to the power of B. So this is SB over 2 order exceptional point, right? Then you can show that this the P operator actually becomes highly sort of singular, because let's say A is just a constant, but B tends to 0. So A over B will tend to infinity, and B over A is tend to 0. So if you were to look at this, if you were to diagonalize this, you always get 0 and 1 as eigenvalues. But if you do a truncation to real space, then you need to Fourier transform these singular terms, and then you actually get something very strange. So it turns out that if you do the Fourier transform in real space, then this UX, which is the 2-point functions or the matrix elements of P, they actually, you can show that they actually become something that has like a log L, depending on the order of the exceptional point. If it's I can show that if it's the first order exceptional point, you get log L. Second order, you get some power of L. And in general, with a B order exceptional point, you get LB minus 1 times something that's very slowly decaying. So this actually these profiles, they have very special shapes. And it turns out that the shape only depends on the order of the exceptional point. So yeah, which means that experimentally, if you were to try to measure them and you get this characteristic shape, you know that you kind of get what you want to see. So these are just some examples of models. Well, I mean, they're just saying that you have, they just represent the order of the exceptional point, and then you can actually numerically see that they have, I mean, analytically predict them to have a certain entanglement entropy scaling. Yeah, turns out that this coefficient of this entanglement entropy scaling, so-called the effective central charge, is linearly proportional to the order of the exceptional points. So numerically, we find that this actually fits the data very, very well. So these dashed lines are the fit, and then the black ones are the data. It just fits very well. But I have to say that I don't really want to call it a central charge, because it turns out that up to now, we still couldn't relate this to conformal field theory. So because I think the likely reason is just that this conformal field theory doesn't predict, it doesn't accommodate exceptional points as far as we know. So far, we couldn't find a CFT that could incorporate sort of exceptional bound states in it. So that means the primary fields and all this, none of them look like the exceptional bound states. So now, I mean, what I want to say is that this C could behave like a central charge that could even be continuously tuned, but so far, I think I don't really want to call it a central charge. Just something interesting is that these exceptional bound states, eigenvalues, also depend on this position of the card in a very interesting manner. So let's say I have a 50 unit cell system, right? And of course, you always have eigenstates of 0 and 1. Many of them, so that it's very dark, means it's highly degenerate. But it turns out that there's always like some like stray branches, like 2 different branches that are away from this 0 and 1. And they are exactly these exceptional bound state branches. So of course, this is symmetrical because if you were to do an entanglement card, let's say you keep, let's say 10 sides, it's the same as doing a card that you keep 40 sides, because it's just that means there's just symmetry between the region, the card region, and the complement. So before I go on, I want to say that this entanglement scaling, that's special. It's not just about modifying the coefficient of log L only by a constant. If you have, let's say, a 2D system, right, it could be even more interesting. So in this system, which we did with Xie Wentan from Wang Zhong's group, I'm an ex-student of Wang Zhong. So we did this work where we consider, let's say, a topological flat bands in 2D that have that's non-Hermitian as well. So that means it's a topological flat band system that has a non-Hermitian skin effect. Yeah. So what happens is that you can think in that, okay, so let's say if you have a flat band system, like there are already many degenerate eigenstates, right? The energies are degenerate already. But imagine if you also have the non-Hermitian skin effect. What happens is that the states will be sort of all pushed to one side, and they will overlap. They have very high overlap, right? So it means now it's degeneracy, so not just in position energy, but also in position, they are almost the same, right? So although this may be an actual exceptional point, but it behaves a bit like a high order exceptional point. And it turns out that this sort of high order overlap, right, give rise to something which we call super volume law entanglement. Yeah. So namely, we are saying that the entanglement entropy can be shown to be exactly like minus half times this B is the order of the exceptional point B times Ly squared log L. So why is this called like super volume law? Right. That's because if you look at the system, let's say if you have a system, let's say the circumference has length L and the entanglement cut region has, let's say, Ly, right? Okay, let's say if you cut, let's say, yeah, then this is the whole cylinder, you cut it off the Ly, right? You might think that because it has a length, the sort of the dimension Ly, that instead of just log L, it could be proportional to Ly log L, right? But it turns out that it's actually not Ly log L, but it's Ly squared log L. Although the length is just Ly, but why is it a Ly squared? It turns out that's because that this extra power of this Ly comes from this like the high order sort of overlap, or the high order like almost like high order effective exceptional point, right? So it means that the order of the exceptional point also contributes to this in a very significant way. And this mechanism, we call it the non-Hermitian critical skin compression. in the sense that the states are all compressed at one point, and if they're also energetically degenerate, they lead to this interesting implications in this entanglement scaling. So I'm going to speed up now. So I promise I won't reach 1.5 hours. So I just want to say that we have done experiments on exceptional bound states, but we didn't measure entanglement entropy. Instead, we just use an electric circuit to mimic this this P matrix in real space, because this is a mathematical property. It's not necessarily entanglement related. And then they are super high. Okay, so yeah, maybe I'll just skip the experimental signatures. If you are interested, you can read our paper here. So it was the actual experiment was done in Zhang Xiangdong's group. Yeah, actually. Okay, so for this part, I just say that, okay, EB states they represent a new type of isolated bound state distinct from topological or skin states. They arise whenever the parent Hamiltonian is defective, and then then there's something called a non-Hermitian critical skin compression, where we could have super volume law, negative entanglement entropy. So if you look at the archive version, the title has a super volume law, but maybe the referee didn't like it, so we removed that part. But because the referee thinks that Ly and L may not be related. Okay, so I think I'm also going to go much faster here. So actually, I have still some slides about this competition between skin effects. Yeah, so maybe I will just briefly introduce the idea about what we mean by competition. Okay, so actually here, okay, so imagine I have a model where I have two Hartano-Nelson chains. One is like, let's say a chain that's going from right to left, and one is left to right, and they're weakly coupled, right? Now you might ask the question, so do they always behave like they're weakly coupled? Or is it possible that even though the couplings are weak, they might behave like a strongly coupled set of chains, right? So the easiest way is to do the numerics. And we see that if the system size is small, let's say n equal to 10, right? The rate is a PVC spectrum and the black is OBC. You see the OBC spectrum is real. But as you increase the system size, the OBC spectrum becomes it starts to become complex. And by n equal to 80 unit cells, it becomes almost like a PVC spectrum. So what this is showing is just that the same system can behave very differently at different system size. And the idea is because when you have these Hartano-Nelson chains, right, it's possible that when they are short, the skin mode doesn't have time to grow, and then they're just they just behave like they're independent. But when it's long, it turns out the skin modes are they grow so much such that even if the couplings are weak, the tunneling is still not weak because the modes are huge. So there will still be some kind of feedback, and then go in the loop. So this is what we call a competition between the non-Hermitian skin modes. And so competition, and this competition, right, if you apply this competition on the 2D system, let's say the topological chiral modes, right, it turns out that you can also have something called the topologically guided gain, where if the system, let's say if the islands are big enough, you have a complex, that means H modes that actually amplify. If not, then that means if the islands are small, then they don't amplify, for instance. So this to understand this from the GBZ perspective, right, I have to introduce an idea called the GBZ fragmentation. So maybe I have to clarify that this is not totally it's not that no one has thought about this before, but maybe this wasn't systematically studied before. So for example, for the Hartano-Nelson model, right, with only let's say the nearest neighbor hoppings, it turns out that if you look at let's say non-block waves actually correspond to an OBC state, you only need a superposition of coefficient of two of them, right? And that's the case for most cases. You just need to superpose two different non-block solutions to satisfy the two boundary conditions, right? So that's how what the GBZ theory was founded on. So if you were to, let's say, look at the log Z contributions to this OBC spectrum, you only see one value of log Z because they coincide. And the GBZ is just circular. But for example, if you have a critical skin effect system, and let's say for example, you make one chain to have larger amplitude than the other, it turns out that your energy spectrum will actually have different parts. It's like this, for example, there will be a ring here that has what we call the different CIPR. That means a different number of contributions. So for instance, like for some states here at the center here, we have this, that means it looks like there are some faint contributions from multiple different values of Z. And the GBZ also, that means that there are not just two rings, but there are some that is like sub-rings. And if you look at the wave functions of the eigenstates, it turns out they actually contribute. That means it's possible that multiple sort of non-block waves have to superpose in such a way that will allow you to create this PBC state, not just two, but many. And if you were to go to a system with many different chains, let's say a random 5 chains, let's say with 5 atoms per unit cell and all many couplings, it's possible that in general the spectrum will just consist of many different random contributions, and that means I'm just saying that in this case the point is that the GBZ formalism kinds of breakdown. That means you no longer have one particular momentum that represents a particular OBC state. Okay. So I think I'm going to conclude now. So basically this GBZ fragmentation leads to this very strong system size dependence of the system and of the OBC spectrum, and you can understand it in let's say when you scale the system, right? That means as the energy eigenstates become more, as you increase more and more eigenstates, right? How where in the GBZ it moves. So let's say in the system, if you have a exceptional point somewhere in the interior of the GBZ, it could be that as you change the system size, right, the GBZ actually it changes, and then it could pass through an exceptional point in the interior of it, right? Such that you get instead of just negative entanglement entropy, you will get a dip in the entanglement entropy. We call it entanglement dip in this paper. And okay, maybe I just went basically it just looks like a system where for small system sizes, it looks like just lump lines. For large system sizes, it actually grows and then it emerges at an exceptional point and it becomes a loop. So this is like a size dependent exceptional point. Okay, so this is a real conclusion now. So I'm just saying that basically when the system has more than one skin effect channels and compete, then you can have very interesting system size dependent effects. But we have this is just at the beginning, because there's still many things that haven't been studied. For instance, all these like curve skin effects in curve space and so on that is not completely understood. So finally, okay, so thank you very much. And as an advertisement, so if you are interested in my review papers, I have 2 review papers here, and you may scan the code. Thank you.
Any questions?
Oh yeah, the high order exceptional points.
It's a high order
You mean this one? This one? Yeah. Okay. So good question. So in this case, right, the B here. Okay, so here, right, let's say the model, the order of the exceptional point is dependent. Okay, so maybe here, okay, let me clarify. So this coefficient has b times ly, right? So b is the order of the exceptional point in the original model. But then it turns out that because you have this sort of very high level, high degeneracy, right? So this degeneracy, that means because the skin compression kind of the compressed, let's say the order of Ly states into, let's say, one side, and let's say to localize at one place, right? So that means the effective order of the exceptional points goes from b to b times Ly. Yeah. Yeah. That means for the origin, that means, let's say if you just look at the definition of the model, it looks like the order is just b. But effectively, because of the skin compression all to one side, so the actual order that means the effective order that the entanglement entropy sees is actually b times Ly. Yeah. Any other questions? Or if you ask the question in Chinese, I'll also be happy to. I can actually speak Chinese.
Second order and fourth order coexistence in this.
In this case, so in this case, I think our model only has that means our model only has the original model with that means the physical model has order b, but then let's say, but because they all compress one side, so it becomes b times Ly. Maybe you're asking whether it's possible to have to generalize it. Is that your question?
Is possible for example, two order and three order or four order together exist.
I think if you're asking about the model, yeah, of course it's possible to write down a model. It's possible to kind of engineer a model where let's say different orders exist at the same time. Yeah, it is possible. But now I think there's actually a subtlety that I didn't talk about, which is that the position of this exceptional point actually matters as well, because you can imagine that, let's say if you were to have a exceptional point at k equal to 0, right? Then the 0 is a long wavelength limit, right? So when we talk about scaling, then of course there's direct implication of a long wavelength limit. But if your EP is not at k equal to 0, let's say if you have multiple EPs, then it's not really the long wavelength limit. So there'll be some oscillations. That means some of the scaling will still exist, but there'll also be some fluctuations just because of this translation in momentum. Yeah. So answer maybe is that you will see similar things, but the effect will not look so nice. Yeah.
Maybe this is non-Hermitian effect where the chain is short. Why PBC and OBC looks very different, but when it goes longer, PBC and OBC looks the same.
Okay. Yeah. So usually it's good if I can draw something, but okay. Yeah. Maybe not in this room. So maybe let me find okay, maybe I can actually this might be okay, actually I have drawn it, but maybe here, yeah. Maybe that's why I skipped this slide much, because I thought I tried to okay, so this is actually similar to what you asked. So if you have a short chain, right? You can imagine that if you have a short chain, the skin modes will just that means when there's a chain, the skin mode will always grow, right? But the difference between a short chain and long chains is that for long chains, the skin mode can exponentially grow much more than the short chain, right? So if you now say that, okay, now you say all the couplings are weak, but if you have a short chain, right, then maybe the skin mode is still quite small, so the coupling is really like a weak coupling. So it's really like the two chains are like not really talking to each other much. But if you have a long chain, then it's possible that no matter how small the couplings are, right, if this is exponentially large, e to the kappa L, right? Then this, even though the coupling is very tiny, but the amount of tunneling can still be quite significant. So of course, then if the tunneling is significant, say let's say the tunneling, let's say I call it T, right? And I call this e to the kappa L as a growth, right? So if T is very small, then it's 10 to the minus 8 or something, very small, right? But if e to the kappa L is actually larger than this T, right? Larger than let's say times T is larger than 1, then it turns out that it could be that you can tunnel, that means the combined effect of the skin amplification and the tunneling, right, could be larger than 1, and it's possible that to form a feedback loop. So you see that if there is a feedback loop, then of course the imaginary part of energy will be different, because imaginary E represents amplification rate, right? So if the feedback loop exists, then your spectrum will have to change that. So in fact, this is like what happens, right? So for this model, this is not hard tunnel, this is SSH, a modified SSH model, where for small system size, it just looks like an SSH model with a dot and some lines. But as you grow bigger, right, I mean, as you increase the system size, the imaginary part increases and it becomes like a two balls, two loops. But for this system, maybe outside of what you asked, but for this, what I showed here is that as you increase system size more, it turns out that it's not just the amplification increases, but somehow the two loops have to touch each other and then they form an exceptional point and then it becomes one loop. But maybe no matter how you see it, it's true that in general, the larger the system size, right, the easier is it for it to feedback loop to amplify, and the larger the imaginary E will be.
To the slide of the homogeneous now.
Oh, okay. This one or?
Yes. I mean, what type of homogeneous are you introduced?
Okay. Maybe yeah. So here I introduce so that means the hopping. Okay, so this hopping, that means for example, the hopping, right, each hopping is given by G times gamma or G over gamma. So one direction is G over gamma, one direction is G times gamma. So in this case, maybe if gamma is less than 1, then it's asymmetric. And this the Gx represents the spatial profile.
They are different, right?
Yeah.
Next slide. Now I still don't know
this one.
Don't know why there is a jump.
Yeah. So yeah.
Picture of this jump.
Yeah. So I think that's a very good question. So what happens is that if you were to, let's say, put this ansatz and you solve you put this into the ansatz into the eigen equation and you get it, you'll get that this, right? And then it turns out that, okay, so here there are two possibilities. One possibility is that this cosine inverse is actually imaginary, right? So that the real part is 0. That's one possibility. Another possibility is that you get two solutions, that means plus minus something. And that's what we see. But now you think, but now let's say I want to, okay, so this is just a theory, but now let's say if I were to look at the actual numerical eigenstate. The actual numerical eigenstate, that means that let's say, for example, now I replace it. Let's say let's say if this were actual numerical eigenstate, and then I were to, let's say, Gx is known, gamma is known, everything is known. So I solve for this kappa from the numerical eigenstate, right? Then I will find that because this kappa is one eigenstate has a fixed value, right? So that means although there are two possible solutions if you solve for it, but actually the actual numerical eigenstate can only choose one of the branch at a time. Because it cannot be two values at the same time. So and then I think what we found very interesting is also that sometimes the numerical eigenstate will just assume one value until suddenly it jumps into another value. And then physically, the understanding is that if the positive kappa and negative kappa represents like a different decay, like a sudden jump in the decay rate, which is like maybe, let's say, so it looks like an impurity, right? Because for example, if let's say this, for example, let's say if you have an impurity here, then you expect that the wave function to have to decay in the opposite direction on both sides. So this is like, so it behaves like an impurity kind of wave function, impurity state. But maybe what's interesting is that although this model, the GX could be very smooth looking, just with some small inhomogeneity, but you still have this sort of impurity state that jumps. So maybe, yeah, maybe I think so physically you can think of it as an impurity, so-called inverted comma impurity state for. Yeah. Oh, okay, but we want to say that, okay, so in our paper, we try to understand this. So it turns out that there is another degree of freedom. So that means that this mod, that means if you were to, okay, let's say if you were to look at this I mean, let's say these branches, right? It turns out that the different eigenvalues, different energies on the branch correspond to different position of the jump. Although it's not just jump, but different energies also have slightly different shapes of this. So it seems like this is like the position of jump. Okay, so to be honest, so we have not systematically tried to study what determines the position of the jump. But from the specific models that we tried, I think the position of jump is controlled by the energy. Yeah.
It means if a state progress is practicing one level is already
something like that. Maybe you can think of it this way. So let's say I have an let's say I take an E1 eigen energy, right? Or let's say E1, or let's say if I were to choose the energy to be one of these values, right? Then this Gx that means Gx, that means at every for every energy, right, you're able to find some region where the Gx is sort of weaker than the energy, and some values of the Gx is stronger, right? So stronger is like the inaccessible, and then weaker means it's accessible. That means, so for example, it could be that for every eigenstate, that means for every eigenstate, maybe you can feel that some parts of this Gx, that means at some parts of the system, this eigenstate is like accessible. Some regions are more inaccessible. And inaccessible, then maybe you could see some, for example, here, let's say between this part, right? This part is when this energy is actually relatively strong compared to this to the Gx. And then when it's strong, that means maybe at the point when it is I think in general, like when it's stronger, like there could be some impurity state. But then when it's weaker, then it becomes some like something like a tunneling part.
Some question, but anyway, long over.
Oh, okay, yeah.
Hour and a half.
Yeah,
Let's stop here and then let us send the again.